Isaac Newton, a young scholar in the midst of the devastating Great Plague, retreated to his family estate at Woolsthorpe. The plague had forced many to isolate themselves, and Newton was no exception. Away from the bustling academic environment of Cambridge, he found himself in a quiet, rural setting. Forced into seclusion, he embarked on a period of unparalleled intellectual productivity. This isolation, rather than hindering him, provided the perfect environment for deep thought and reflection. It was during this time, between 1665 and 1666, that I developed my groundbreaking ideas on calculus, which I termed fluxions. These ideas were revolutionary and would later form the bedrock of modern mathematics.
Newton's approach to calculus was deeply geometric. He saw the world through the lens of shapes and forms, and this perspective was crucial in his development of new mathematical concepts. He envisioned curves as being generated by the continuous motion of a point. This dynamic view of geometry allowed him to think about change in a novel way. He called the rate of change of a curve's position fluxion. This term, though archaic now, was a cornerstone of his mathematical framework. This concept formed the foundation of his differential calculus. Newton's work in this area was pioneering and laid the groundwork for future mathematicians. However, Newton, notoriously reticent, did not immediately publish his findings. His reluctance to share his work meant that his groundbreaking ideas remained largely unknown for many years. This delay would later become a point of contention in the calculus priority dispute. The academic world would eventually recognize his contributions, but not without significant debate and controversy.
Across the English Channel, I, Gottfried Wilhelm Leibniz, a German polymath, was independently developing my own version of calculus. My journey into the world of mathematics was driven by a deep curiosity and a desire to understand the underlying principles of nature. Unlike Newton, whose work was shrouded in secrecy, I believed in the power of sharing knowledge and collaboration. My work, conducted in the 1670s, differed from Newton's in both notation and approach. While Newton focused on the physical interpretation of calculus, I emphasized a more abstract and algebraic perspective. This distinction was crucial in shaping the future of mathematical analysis. I emphasized algebraic manipulation and the concept of infinitesimals, infinitely small quantities that represent the difference between two values that are infinitely close together. This idea of infinitesimals was revolutionary and allowed for a more flexible and powerful approach to solving mathematical problems.
Leibniz developed a system of notation that used dx and dy to represent infinitesimal changes in variables. This notation was not only elegant, but also highly practical, making complex calculations more manageable. His notation, with its intuitive symbols like the integral sign and the derivative notation, dy dx, proved to be more accessible and adaptable to a wider range of mathematical problems. This system of notation became the standard in mathematical analysis and is still in use today. This accessibility contributed significantly to the rapid spread and adoption of Leibniz's calculus across continental Europe. The clarity and simplicity of his notation allowed scholars and students alike to grasp complex concepts more easily, fostering a new era of mathematical exploration and discovery.
The stage was set for a clash of titans. In the late 17th century, whispers of Newton's unpublished work on calculus reached Leibniz. This exchange of ideas, though indirect, ignited a bitter dispute over priority and originality.
The Royal Society, the preeminent scientific institution of the time, became embroiled in the controversy. Accusations of plagiarism were leveled, with Newton's supporters claiming that Leibniz had stolen ideas from Newton's unpublished manuscripts. The Royal Society, under Newton's influence, formed a commission to investigate the matter. The commission's report, published in 1712, sided with Newton. However, the controversy continued to rage long after both Newton and Leibniz had passed away.
The rivalry between Newton and Leibniz had a profound and lasting impact on the development of mathematics. Their different approaches to calculus, reflected in their notations, shaped the way mathematicians approached and solved problems.
Newton's notation, though powerful, was considered cumbersome by many. His dot notation for derivatives, while elegant in its simplicity, proved less versatile than Leibniz's more symbolic notation. Leibniz's notation, with its intuitive symbols for integrals, derivatives, and infinitesimals, gained wider acceptance. It facilitated the development of new mathematical concepts and techniques, paving the way for advancements in fields like physics, engineering, and economics. Section 5. Philosophical underpinnings, empiricism versus optimism. Beyond the purely mathematical, the Newton-Leibniz controversy also reflected a deeper philosophical divide. This divide was not just about numbers and equations, but about the very nature of reality and how we come to understand it. Newton, a staunch empiricist, believed that knowledge stemmed from observation and experimentation. He argued that the only way to truly understand the world was through direct experience and empirical evidence. Leibniz, in contrast, embraced a more metaphysical view. He believed that reason and logic were the primary tools for understanding the universe, and that empirical evidence was secondary to rational thought. His optimism, the belief that our universe is the best possible one, permeated his work. Leibniz's philosophy suggested that everything happens for a reason and that the universe is inherently ordered and good. This philosophical difference influenced their approaches to calculus. For Newton, calculus was a practical tool, a means to solve real-world problems and describe physical phenomena. Newton viewed calculus as a tool for describing the physical world, a means to understand the laws of motion and gravity that he so eloquently articulated. His work laid the foundation for classical mechanics and had a profound impact on the scientific revolution. Leibniz saw calculus as a reflection of a harmonious and rational universe, a testament to the power of logic and reason. He believed that mathematics was a language of the divine, revealing the underlying order and beauty of creation. Section 6. Calculus, the language of the universe. Despite the controversy surrounding its origins, calculus emerged as one of the most powerful and versatile tools in the history of mathematics. It provided scientists and mathematicians with a new language to describe and analyze change and motion. Physicists embraced calculus to formulate laws of motion, electricity, and magnetism. Engineers used it to design bridges, buildings, and airplanes. Economists applied it to model markets and predict economic trends. Calculus became an indispensable tool for understanding the natural world and for advancing technological innovation. It transcended the boundaries of mathematics, influencing virtually every field of science and engineering. Section 7. Modern manifestations, from AI to algorithms. The legacy of Newton and Leibniz's calculus extends far beyond the 17th century. Today, their invention underpins countless technologies and innovations that shape our modern world. Artificial intelligence, for instance, relies heavily on calculus.
Machine learning algorithms used in everything from self-driving cars to medical diagnosis are built on the foundations of calculus. Algorithmic trading, another example, leverages the power of calculus to analyze market data and execute trades at lightning-fast speeds. From predicting stock prices to optimizing investment portfolios, calculus plays a pivotal role in modern finance.
Section 8. A legacy of innovation and rivalry. The story of the calculus wars is a testament to the power of human ingenuity and the complexities of collaboration and competition in the pursuit of knowledge. Newton and Leibniz, though separated by geography and temperament, made groundbreaking contributions to mathematics. Their rivalry, while bitter and protracted, ultimately enriched the field of mathematics. It led to a deeper understanding of calculus and its applications, paving the way for centuries of scientific and technological progress. The calculus wars serve as a reminder that even amidst controversy and rivalry, the pursuit of knowledge can lead to extraordinary breakthroughs that shape the course of history. Section 9. Conclusion. The enduring impact of the calculus wars. The calculus wars, a clash of titans and ideas, left an indelible mark on the world of mathematics and beyond. It highlighted the power of notation, the importance of collaboration, and the enduring impact of philosophical differences on the development of scientific thought. Newton and Leibniz, through their independent yet intertwined journeys, bequeathed to us a tool of unparalleled power and versatility. Calculus continues to shape our understanding of the universe and drive technological innovation, a testament to the enduring legacy of the calculus wars.